Solving an absolute value inequality is going to have a lot of the same characteristics as solving an absolute value equation. Here we have an equation that we would have solved by splitting into two separate problems. One of the problems would have said that 5x minus 1 is equal to 9. The other, 5x minus 1 is equal to negative 9. And we did that because there were two different ways to make this expression end up having an absolute value of 9, whether the expression was equal to 9 or negative 9. We solve these as we would any equation, and we end up with the two separate solutions that make this equation true. When solving an inequality, we'll use much of the same skill set. So here's an obviously very similar inequality to the equation that we just solved. We have the characteristics that we're looking for. Just like with equations, we want the absolute value to be by itself. So we'll split into two separate questions. On the left, we'll split for 5x minus 1 and 9. And on the right, we'll split 5x minus 1 and negative 9. Now, the obvious difference, there being an inequality in this question, means there's going to be a difference in this separate solution path, in these separate solution paths, In order for our absolute value to be greater than or equal to 9, we are going to need the inside argument of the absolute value to be greater than or equal to 9. Or, in order for my absolute value to be greater than or equal to 9, I'm going to need my inside argument to be less than or equal to negative 9. So if you're picturing the number line and where these solutions would fall, this is very clearly going to fall in a situation where we'll have solutions outside of a particular region. And that's exactly what happens. So we're going to add 1 and divide by 5, and we get x is greater than or equal to 2. And on the right, we're going to add 1 and divide by 5, and we get x is less than or equal to negative 8/5, also known as negative 1 6/10. If we're picturing this on a number line, we'll have 2 over here, we'll have negative 1/6 over here. We want to be greater than or equal to 2. We want to be less than or equal to negative 1 6/10. This is very clearly an OR situation where we have numbers outside of those regions that are the solutions. And if you really want to convince yourself that those numbers are the solutions, feel free to pick a number from those shaded regions and try them. If I tried 3 from over here, I would get 14, which is obviously has an absolute value larger than 9, And if I tried a number from over here, say negative 5, 5 times negative 5 is negative 25, minus 1 is negative 26, and that absolute value would also be larger than 9. Because of the inequalities requiring us to go outside of a particular region, we notice the very obvious relationship between this solution and an OR compound inequality. And that's truly what we should anticipate happening. If we need to be greater than a number, we're going to have to look to those spots outside of that interior space for the numbers that are going to work for this inequality. Similar to that last example, but in this case we have an extra operation that we need to do. We're going to go ahead and move that 1 over to the other side, and then we're going to split again. In order for my absolute value to be greater than 5, my argument must be greater than 5, or my argument must be less than negative 5. Solving both of these, I get x is greater than negative 1, and over here I get x is less than negative 3. And my hope is, because I see this greater than, my hope is that my two solution paths will follow an OR look. They will look like an OR compound inequality. And that's exactly what happens here. Negative 1, negative 3, I'm less than that, I'm greater than negative 1, I'm outside of those two numbers. And if you want to convince yourself that the interior doesn't work, feel free to try a number that's on the interior of that space, something like negative 2. 5 times negative 2 is negative 10. Negative 10 plus 10 is 0. So you would get 0 out of here. minus 1, that is certainly not bigger than 4. That does not work. That's not a part of the solution. So we anticipate, again, solutions on the outside, thanks to that greater than that we started with. Contrast that to this example where we start with a less than. We'll perform the same first operation. We will isolate our absolute value. We will see that we need our absolute value to be less than 3. If I need this argument in here to have an absolute value of less than 3, there's 2 ways for that to happen. I can be less than 3, and I can be greater than negative 3. That's a hard visual for a lot of people because if you're thinking that I'm greater than a negative number, you're automatically thinking, well, if I'm greater than a negative number, I'm all the positives. But this inequality here on the left is going to work together with this inequality here on the right to form that very defined region where we're going to find our solutions. 5x is less than negative 4, x is less than negative 4 over 5, and 5x is greater than negative 10, x is greater than negative 2. So I want to be greater than negative 2, but less than negative 4/5. I want to be in that space in between those two numbers. Now, as just a reminder, I may want to write this using interval notation. I want to get into the habit of using interval notation more and more when it comes to writing the solutions of these absolute value inequalities and compound inequalities. So in our interval notation, we're going to go from negative 2 to negative 4.5. We notice that on the ends of both in the interval notation that we're going to use open parentheses, or not open parentheses, the soft parentheses, the ones that are not the brackets, because we don't want to include negative 2 and we don't want to include negative 4/5 in our solution.